for the URL. I've got truncated a little. Okay. All right. And today it's my great pleasure to introduce Professor Angelos Keromytis from the Department of Computer Science at Columbia University. Angelos is a assistant professor of computer science at Columbia, and he received his master's and PhD from the University of Pennsylvania and his bachelor's degree from the University of Crete in Greece. His research interests include network and system survivability, authorization and access control, and large-scale system security. In a previous life, Angelos had enough time to contribute code to the OpenBSD project. So without further ado, Angelos.
Thank you. I would have spiced it up if I knew you were going to actually read that. But anyway, this will do. So thank you for coming at this fairly late hour during the day. And what I'm going to talk about today is some initial steps in our work to create self-healing software. And by self-healing, I mean a very ambitious vision of software that can identify failures of many different kinds and automatically take steps to correct them. So if you were here for the whole story of copying files back and forth, that ideally 20 years from now when we solve all the problems, I'd like the system to figure out what it is that I want to do and do it, but we're a long ways from that. So the summary of the talk, and you have to forgive me for the slides not quite fitting here, but that was the problem that we're trying to deal with, was that we're trying basically to create software systems that heal themselves against failures, whether they are security attacks, whether they're bugs due to program mistakes, with as little or no, ideally, human interaction. So if you're going to fall asleep for the rest of the talk, that's the message I want you to take away, that, especially if you fall asleep, that these guys at Columbia really solved this problem. If you're awake, then, okay, you get to hear what we actually did. And so in doing so, we're really motivated by the current situation in the realm of software security, where basically the attackers hold all the advantages, which is they have the advantage of selecting the place and the time to strike, which is the traditional advantage in all conflicts in history. The attacker gets to choose where and when to attack. Well, mostly when. And also they get to exploit large numbers of compromised systems to further enhance their attacks. And also, to a large extent, they exploit the fact that we all run the same version of the same operating system, or a fairly small number of operating systems and applications. And so all they have to do is find one vulnerability, and then they can write code that helps them automatically exploit that vulnerability in many millions of instances of that same piece of software, whereas we, the good guys, to the extent that we are the good guys, can't really or haven't figured out yet how to exploit automation to our benefit, at least to the same extent. Of course, this vision is very, very ambitious, and it raises several questions on whether it's even possible. And even if it is, in principle, feasible, whether it's practical, and then what are the trade-offs? Because as everything in computer science, we're giving away something in return for something else, right? Computer science all about engineering, making it somebody else's problem or hiding the problem somewhere else. Now, although I come from a security background, my and the work, and some of the work specifically I'm going to talk about here, focuses on a very security-specific set of concerns. In fact, the scope of the project is much bigger than just security, as I said earlier. We really are trying to enable software to deal with all kinds of failures. And for now, I'm going to define failures are very low-level software faults, which when you see them, you know they happen. So when your Internet Explorer crashes, you know that something bad happened, right? So you don't really, intuitively, you understand that this is a fault. So that's the kind of failure that we're going to be looking at. And then towards the end, I'm going to give you some sort of blue sky thoughts as to where we can go with this. And remember, the focus is always on software, in contrast with other work in this area of autonomic computing, as it's called, that tries to abstract away system components as black boxes and then try to move them around or reconfigure them and so on. We really are trying to peek into the software that somebody else wrote. All right, so the overview of this talk is I'm going to start by scaring you witless with the state of software security by citing some statistics from CERT and other agencies, other acronyms. And then I'm going to give a very quick overview of related work, what's happening in trying to protect against various types of software vulnerabilities and software-based attacks. And then I'm going to present the motivation for our work, self-healing software. What do I really mean by this? And two particular techniques that we developed that enable us to address a large class of software failures, and those are called microspeculation and error virtualization, very catchy names. And then I'm going to talk about how we use those two techniques in two specific systems, the worm vaccine architecture, which as the name implies, is aimed at dealing with the problem of network worms specifically, and then the STEM system that's addressed at a larger class of software type of faults. And finally, if I have time, I'm going to talk a little bit about this new concept we've started working on, which is application communities. All right. And at any time, feel free to interrupt and ask questions. I may not answer them, but feel free to ask them anyway. So what's the state of the union? Basically, you don't need me to tell you that we use a lot of software and increasing amounts of software, right? Every release of Microsoft Windows or any operating system or any application just adds more code. So not only we inherit all the previous problems that code had, we get the benefit of more places where failures might occur, and we depend on this software increasingly, right? So all sorts of systems are moving away from pure hardware and mechanical relays and things like that to fully automated software control infrastructures. Unfortunately, even though we depend more and more on software and computing artifacts, the quality of the systems, and in particular the quality of the code, hasn't really improved as much or at all for that matter. So what that means is that we open ourselves increasingly to being vulnerable to more software vulnerabilities, more software failures, whether they are accidental failures, program just crashed because the programmer didn't know what they were doing, or there was some kind of logical flaw that an attacker managed to exploit. So very, very brief example of what I mean, the kind of failure that I mean, buffer overflow attacks. It's probably beaten to death, but I'm going to very, very quickly go over it because the example I'm going to use it later. So you have the code on the left, which is this hypothetical routine that has this array called overflowed that hints as to what might happen to it later on, statically defined fixed size, and then we use it unsafely to copy one string to this array. And what might happen here is on the top is the program stack. This is the standard model of an operating system, what a process looks like in its private address space, right? The program stack grows lower, and what happens when the caller, in fact, is on the stack, sorry about that, when the caller is on the stack, we have the stack frame for the caller that identifies where the caller needs to return, where the caller needs to return when that code finishes executing, where the return value needs to be placed, all the arguments, so overflow is going to be over there, and so on and so forth. And when it calls string copy, there's going to be another stack frame that's going to point to the corresponding information for string copy. Now, what the buffer overflow does is, because string copy in particular doesn't check that the input, the source buffer matches is at most as big as the destination buffer, what might happen is string copy might continue overwriting past the end of the buffer and start overwriting control information that's on the stack. In particular, in this case, the return value, and more importantly, the return address. So that means when string copy gets to return, it's going to use information that was in fact contained on the source buffer. So if that is some kind of